Hello, I'm Zara, and today I'm going to review a paper that has a title Stress Analysis of Aspherical Tracer Coated Particle with X-ray Computed Tomography. In this paper, we want to know how does the asphericity affects the failure of coated TRISO particle. Uh, we know that the stress that is applied to the particle is important to be considered because from the simplification, the distribution, the stress distribution analysis is done based on the pressure vessel model uh, only in which we only consider silicon carbide layer. We assume that the particle coating will be undergoing a failure whenever the silicon carbide is received stress that is exceeding its tensile strength. The problem is in the real condition, the particle it's not the shape of the particle it's not really asparis. There are some deviation from the spherical shape, and we call that aspericity. Models like Panama, Perfume, Himcot, Pasta, and Atlas is assuming that the silicon carbide is is a sphere. So we use finite element method to examine the effect of asphericity to the stress distribution, and we use X-ray computed tomography to obtain a three-dimensional image from the geometry of the silicon carbide. And from that image, um, we examine the thickness of the layer and we compare it with its design value. So we move to the material and methods. The computed tomography will be dividing particles into hundreds of slices, and those slices will be imported to the Amira software to reconstruct the three-dimensional volume of silicon carbide layer, and the silicon carbide layer will be imported to the abacus to simulate the stress distribution. We know from the maximum curvature distribution of silicon carbide will be showing its aspericity. Uh, and from that data, we have average measured thickness that is 39.283 micrometer with the deviation standard is 1.228 micrometer, and the difference between the measured thickness and the design one is 13.283%. And in this and in this paper we divide silicon carbide layer into 78,601 mesh. So this is the result from the city slices, and we can see that this coated particle it's not really a sphere, but there is some aspericity that happens to the coated particle. So this is the result from three-dimensional film rendering, A from the x-axis, B from the y-axis, C from the z-axis, and D from all of the axes. And here we have the distribution of silicon carbide thickness and the maximum curvature of silicon carbide. Analytically, we calculate stress based on the Panama model, and here is the equation with sigma sub t is the average tangential stress on the silicon carbide layer, and r sub m is the silicon carbide's average radius, and d is the silicon carbide initial thickness, and p sub 1 is the inner gas pressure. We also use perfume model, and in this model, we thought silicon carbide layer as an isotropic elastic medium. And this model is used for um, finding the tangential stress as well. And here's the equation with R is the radius, P and Q is the inner and outer radial stress on the silicon carbide. R sub A and R sub B is the silicon carbide inner and outer radius. We also use the soft bubble approximation in which we only consider inner gas pressure and neglect the radial stress on the silicon carbide. Here is the cumulative distribution function based on Weibull theory to calculate the failure probability or F sub v for coated particle with the sigma sub c and sigma sub ms is the tensile strength stress and the average fracture strength of silicon carbide, and m is the perimeter Weibull. So we measure the kernel diameter and the thickness of the coatings, and there are some differences in value with the design one because there is some uncertainty on its manufacture. And we can see that there are positive and negative values on here, and the positive ones indicate that the actual diameter or thickness is actually larger than the design one, and the negative ones indicate that the indicate that the actual diameter or the thickness is actually smaller than the design one. So in these results, we compare the differences in stress on the silicon carbide actual shape with the ideal one, with the ideal one is being spherical, and we reconstruct the the spherical layer of silicon carbide based on design value and then simulate it with the same condition. So we also compare the maximum stress value from analytical results and the simulations result as well. Now that the silicon carbide layer will be dividing into 78,000 of nodes, and from each node we calculate the stress distribution. And here are the simulation condition with which we use 460 GPa of elasticity modulus, and the ratio Poisson is 1.221, and the inner gas pressure we use is 17 MPa. And we obtain the maximum stress on the silicon layer is actually one 154.8 0.298 MPa. So here we have the maximum stress distribution as a function of the silicon carbide thickness at different radial directions from the inner radius to the outer radius. We have differences in thickness because of the manufacture factors, and the differences in stress on the actual shape and the spherical one is um, 5.258%. So in this result, we also compare the stress result from each method, like from the finite element method and the Panama and the Farfim one. We have the degree of stress concentration here, and uh, this is the ratio between the maximum stress to the uh, average stress, and this degree is indicating there is some asperity. So here we obtain a stress result on the actual silicon carbide layer as a function of inner gas pressure, and we can see that the maximum stress on the actual silicon carbide layer is actually larger than the calculated ones from the analytical methods. And we have to note that the average of actual silicon carbide layer thickness is actually larger than the designed one, and meanwhile the average stress value is always smaller than the analytical ones. Here on the left side, we have the maximum principal stress as a function of Poisson's ratio for different inner pressure, and on the right side we have the maximum principal stress as a function of elastic modulus for different Poisson's rate. So here we have assumption: if the tangential stress exceeds the tensile strength of silicon carbide layer, the coating layer will be thought as failure. We obtain maximum stress and average stress for calculating the probability of failure or failure probability. And this probability for this simulation results and for the analytical ones are increasing as the gas pressure increases. And the differences in probability can be neglected if the gas pressure is under 10 megapascal. To wrap things up, there is an increase in stress whenever the layer thickness is increasing, and that is caused by uh, local concave or convex on the silicon carbide layer. And this local convex or concave is are caused by the manufacturer defects or the slicing process. And we have to take a note that this result is only for one particle, so we can investigate some numbers of particle for further research. Uh, that's all from me, and thank you.